Okay, so I will describe rather briefly what is this package we began developing together with David, which is called TaylorModels.jl, and you can find it here. So the package is, first of all, not mature enough. There are certain holes, but actually there are a couple of things that does correctly. And this is, at least at the beginning, what it matters. So let me begin. I will explain first what are the Taylor models. So they were introduced by Beat, Makino, and both together, 20 plus epsilon years ago. Now, the idea is, instead of dealing with intervals and a very complicated function f of x in a given domain, which is the interval you care about, what you do it is, instead of using the interval evaluation, you exchange that function by a Taylor polynomial, which is this p of x of a given degree. You can play with the degree later, which you are creating by expansion around a given point inside the domain, and together with a remainder. So a bound of the error that you are actually performing in, by going from this f of x to the polynomial. And in a way, what I described means you need a tuple of 4 elements: the polynomial, the remainder, the bound, the expansion point, and the actual domain. So the Taylor polynomial we computed using Taylor series. I will skip all the details. Let me only say that the coefficients are precisely directly related with the function, and what we have in Taylor series is pretty general, but not actually too general, or not universal, if you wish. Now, in order to find a valid bound, what you need, what we use is essentially Taylor's theorem, which means use the Lagrange remainder. And Lagrange remainder is take the next derivative of your order. So if your expansion is up to order n, then you go to, this should read n plus 1 everywhere. And you evaluate, Taylor theorem states that there is a point inside the interval where this expression is exact, so you make no error. But since you do not know this psi, then you replace it by the whole interval. And then you have to evaluate that derivative, the next derivative in the whole interval, multiplied by this thing, and this gives you the remainder. And there are a couple of things. The idea is to guarantee that f of x is inside that set for all x in the domain, and second, that the remainder contains 0. And this second reason means that actually there is a point inside where you have the exact solution. Now, Mioara Yoldes, a few years ago, also introduced, or generalized, if you wish, the Taylor models to the so-called Taylor models with relative remainder. And the idea is that you have not a constant remainder, but you have some sort of relative remainder by adding this next order coefficient in the Taylor expansion. And I will not go into lots of details, but actually I think it is a beautiful idea, and I think it should be exploited further. We have an implementation. Not everything is implemented with these Taylor models with relative remainder. The whole thing it is that they actually allow you to consider functions with removable discontinuities. So I will present an example. How does this thing work? And now what you need, at least before going into coding how elementary functions should be defined, is that you need the basic arithmetics. And let me just go with the addition and multiplication. Addition is quite trivial because you add polynomials and then add the remainders. And multiplication is a bit more subtle, and actually it is part of one of the particularities we have. The polynomial part will be the truncated multiplication up to a given order, the order that you are fixing of your polynomial, so say n. And then the remainder consists on a lot of terms. And this definition means that you have to somehow be able to have either a good guess for this remainder, or I mean this part of the remainder, which is all the higher order terms beyond n in the polynomial multiplication, or you have, I mean, which we're actually computing currently, or you have to do much maybe coarser constructions, which could give some speed ups. Sorry. So let me illustrate a little bit how this thing works. So you need to define a domain. You need to define an expansion point. In this case, it is a floating point, floating 64 point. And then you simply, in this case, I am creating a one-dimensional Taylor model variable of degree 2, which is an expansion. This is some sort of identity around x0 on the domain DOM. Okay, and it looks like this. So in this case, I have 0 remainder. So how do you use it? You compute simply a function and it gives you the result. And now this is actually a tight bound for this exponential function up to degree 2 in the polynomial expanding around 0. I didn't say anything about how to do all these tricks about the functions, but inside is Taylor series magic, and inside that actually it is a very, very close relation with whatever, I mean, with the ordinary differential equations, which makes it very appealing to work on validated integration of ODEs. So you can do exactly the same for these Taylor models with relative remainder, and it simply works. And the only thing I want to emphasize here, it is that the remainder here, it is some sort of order 0 in the Taylor polynomial, whereas here it is the next leading order, I mean, next order in the Taylor expansion. So in a sense, the relative remainder, it is in this case a third order expansion, whereas in this case I had a 2-order expansion for the absolute remainder case. And let me, I don't know why the plot didn't appear. Maybe I should have run everything, but let's forget it. That is a pity. Anyway, so how do we compute everything? So what we first do, it is that we consider that the Taylor series expansion, this is in TaylorSeries.jl, of the function we care. So this is the Taylor series up to order 2. Now we compute another Taylor expansion, but not around a point x0, but around a domain. And that, I mean, it is up to order n+1, not order n. So the last coefficient is actually the derivative evaluated in the whole domain. So we need that coefficient and this multiplication simply, simply to evaluate the remainder. Now, if you recall a little bit the numbers, this is actually wider than the remainder I was presenting before. And actually, you can optimize the remainder with some tricks. And for instance, this is not the case here. Sorry, this is the case here. That that this coefficient, this fn+1 on D, has once, I mean, it is always positive. And that means that in a way that you have certain properties of the monotonicity of the remainder, and you can exploit them to bound better the range of the actual Taylor model. So I think I will not be able to show the plots by some reason, but let me go to, again, with this function. This has, I mean, a removable singularity. If you notice, x minus x to the third over 6 is essentially the first two terms of the Taylor series of sin of x, and this -1 gives you the error that you are actually performing on this expansion. And I will be doing the expansion around the 0 value in a symmetric domain. So if I do it with normal interval arithmetics, I get a -infinity to infinity that someone was commenting what should be the proper result for the division. If you do it with Taylor models with absolute remainder, you get an error. And an error is a bit cryptic. That's my fault. Never mind. But the point is that you're evaluating a Taylor expansion, dividing things, and you have some sort of singularity in the, well, a zero in the denominator, and this cannot be done. So what is the contribution then of these relative remainders? Well, it simply works. I mean, you get a zero because essentially what you do is that you factorize the leading order terms, you cancel them out, then you get constant factors, you can expand, then you get a zero, and then you get a remainder with, I mean, this t to the third coefficient. And by some reason, the plots are not appearing. Maybe I forgot to run it. Now, this is from the PhD thesis of Makino, which is a long way back, and it is a polynomial, and the idea is to bound it in the 0-1 range. And this is the exact, well, more or less the, say, approximate, I think it is exact approximation for the range of that function. So how do we do it? So this is the direct evaluation with, direct evaluation with interval arithmetic. And you get a very wide range. And the problem, as David described before, it is that you have more than one instance of these x, and they are taken as different, and then, I mean, you get into over approximations that you don't quite like. Now, if you would do Taylor models very naively, and let me emphasize very naively, so expanding around zero for that domain, then the expansion of a polynomial is a polynomial, so you get the same answer. So whenever you evaluate this polynomial, again, you will have this 0-2 range, so no help at all. The point I want to emphasize here, it is that Taylor models allow you to play with the expansion point. And that actually helps you to constrain the range quite a lot. So let me take the midpoint, which is always very positive. So you get lots of good things out of that. And I mean, you still have a fifth order polynomial for the polynomial expansion, but now that you evaluate on the actual domain recentered, then you get a much better approximation for the range. So this is the kind of thing where Taylor models may play an interesting role. Now, simply, I would like to go into a very sort of complicated example. I don't think that the whole function is clear now, which is, I mean, a function on 3 variables, and you have a sort of narrow range somewhere in the plane. Now, this is the code of the function, and to work with Taylor model in n dimensions, which only work with absolute remainder so far, you have to set up a couple of things. This is not too nice. This is, again, my fault, but never mind, it works. Now, let me notice that I will be dealing with order 3 polynomials, up to order 3 polynomials, and I need to define these internal variables up to order 6. And this is due to the way we are actually defining multiplication. So since we are dealing with polynomials up to degree 3, then the multiplication of 2 polynomials will be up to degree 6. And I mean, so this certainly has a hit in the performance. So far, it is good enough. But I mean, this is a place where things can be improved. I defined the interval box around which I want to expand. I defined the domain, and these will be my Taylor model n independent variables in each direction. Sorry. So this is the direct evaluation on those variables, and you see that you get, I mean, sort of a tiny remainder. And if you now compute the range, then you get a very nice result. Now, just to compare this against naive interval, I mean, the naive use of interval arithmetic, then this yields a much wider range due to obvious reasons, which are related with the dependency problem. Now, I do not know how much how am I doing with respect to the time. Do I have some time, or shall I cut here and then we later discuss about this?
Continue.
So
continues, yeah.
So as I mentioned very briefly, I mean, we have some implementation, and the use of Taylor models actually, it is to deal with this validated integration of ODEs. So the ODE is the common setup. You have a differential equation, you have an initial condition, you may have parameters, you may have on say intervals on those parameters or on the initial conditions. I will not go into those details, but I mean, we have managed to work all those particular cases in the package. So the idea of using Taylor models is you sort of expand your solution as a Taylor expansion on the independent variable t. So you have this thing. And these are coefficients which are related with the derivatives of the function. And this is sort of uncomfortable to compute, but I mean, there are ways exploiting automatic differentiation of high order to get them, and this is what Taylor series does. Now, you have to somehow have a guess of what is a good time step, and we're using the time step provided currently by Taylor integration, which is not validated. And then you come to the last step, which is the crucial one. And Benoit was mentioning that you somehow have, I mean, that there are nice properties if you have some sort of fixed point problem. So this operator on the right of this equation is a linear operator. And the idea is that this is somehow contracting. And contracting means that, I mean, when you put here a bound, somehow this is contained in the actual thing that you are putting in here, which is all this. I mean, so this is your candidate of the solution, and you want that this Picard-Lindelof operator contracts and is contained on the original one. If you have this property, then you can ensure that the solution exists and is unique. And what we have currently are some, I think, very good heuristics on doing this thing, but it is not fully validated. So I should simply say so, but you can look at the code and notice where the weaknesses are. And as an example, I will use the Lotka-Volterra system, prosum tangential crossing, so you can define some a priori boundaries where things can, I mean, some guards in the language of hybrid systems and all that. And I will be using reachability analysis because, I mean, Marcelo and Christian have actually thought a lot about having a nice API. And I mean, I will use it. It is much nicer than the one we have. And also Benoit was mentioning that for interval root finding, maybe we should rethink things. So these are a couple of, I mean, things that you need at the very beginning. This is a key ingredient if you want speed, or at least if you want to improve a little bit speed. So we need this macro currently, and not only this macro, but you have to, say, factorize things that you use, say, a couple of times. And this is only to avoid repetitions and, I mean, lots of allocations and all that in the integration process. Now, this is the beautiful API defined by Marcelo and Christian. And what we did for this specific case is that we minced. So we considered a bunch of tinier intervals, and we simply broadcasted the solution. I mean, the problems first, the definition of the problems, and second, the solutions of the problem. And I think I will not be able to show the plot if you give me 3 minutes or so. I have to maybe run the notebook, which I might have forgotten. And the point is that, I mean, well, once we produce all the plots, we have a validated or quasi-validated solution, and we can add guards, even nonlinear guards, and there is a bunch of tricks to exploit, I mean, the boxes we have, the Taylor solutions we are actually having to end up with plots like this. And with this, I'm done. And well, thanks again, all the organizers, for giving me the chance to talk here.
Cool. Cool. Thanks a lot. Now, you could also, do you want to comment on the colors of this very nice plot that you obtained in the end?
Oh, then I should share again. So the validated solution, or the solution, the quasi-validated, I think it is proper language for this, it is the blue one. On top of that, we are coloring things that actually get into this boundary, this nonlinear boundary, which are actually almost tangential. And you see these green or greenish blocks, which are entering in the upper part, and then the orange blocks, which are entering in the lower part. So I guess this can be reformulated in the contractor's language. I have no idea how to, but anyway, this is the way things done. And maybe now that the plots are there, this is the plot of this relative remainder Taylor model. So this is the function I was trying to approximate with a polynomial, and this is the error. And what you see is that the error depends on where are you in the domain that you are actually trying to approximate. So from time to time, towards the edges, you have a worse error than towards the middle. Yeah, David.
Very nice talk, Luis. Yeah, great work. I was just wondering if you could say exactly why you say it's not completely validated.
Yeah, that's a bit embarrassing, but anyway. So let me maybe share again. So I guess, where am I? Well, anyway, I don't know what's going on here, but well, something happened with my presentation, or maybe it is running again. Sorry. Let me find yeah. So I'm not sure whether you can read the contraction property. Now, the contraction property involves directly Taylor models. So you have to deal with evaluating this function on the Taylor models. And the Taylor models that we are trying to produce are the Taylor models on one variable, which is the time variable, so the independent variable as t here, but also all the coefficients are, say, Taylor models on the initial conditions, say, or on the initial box, or whatever parameters you have. I mean, these are Taylor series with with coefficients which are polynomial in other variables. And it is extremely costly to compute, I mean, this function on this Taylor model 1 of Taylor model n. So what we are doing is actually doing some heuristics, which most of the time work, but not all the time. Essentially, that's the crucial part. I'm not sure whether I clarified it or not, but that's the actual problem we have.
Okay, thanks. Do you know how other tools solve the problem?
Some of I can tell you the way I think we could solve it in Julia, and the way it would be to generalize in a way this Taylorized macro. Now, I remember that we spoke about these kind of things of using symbolics long time ago. The same idea, I think it could be applied here. So in a way to propagate symbolically the remainder and simply exploit it at the very end. For that, I mean, when you are evaluating that operator, that contraction property. I've been thinking about doing it the way I did it for Taylorize. I think it is doable, but there are some parts which are not working so nicely yet. I have some work somewhere in my computer, but yeah, I mean, the idea is there. Now, I think other tools, which I think it is Flowstar, if I recall correctly, they do something like that. So they sort of analytically propagate the remainder and eventually grab that up in and only evaluate it at the very end.
Okay, thank you.
So if I may have a question, so thank you very much for the presentation. But, would you consider providing one or two specific examples from the real world where Taylor models are used or maybe potentially used? I don't know how to say it. By real world, I mean, maybe not scientific computing nor numerical mathematics, but rather like very practical use case, like, I don't know, just guessing autonomous vehicles or maybe economic forecast models, like something that like would be easy to example that would be easy to understand for a person who is not mathematician.
Okay, so I'm also not a mathematician, I must admit it beforehand. Anyway,
Okay.
The idea, as far as I recall, the idea of BERT was to use them in the dynamics in the reactors.
Okay.
And as far as I know, they have used them there. Also, some other groups have been using them in these chemical kinetic reactions. I have no idea what I am saying. But the point is that there are real world examples where this type of say, validated tools have been used. I think maybe Marcelo or Christian can provide other examples, I mean, with for robots or things like this. But a priori, if you have a reasonable, when I say reasonable, I mean the number of dimensions cannot be too large, then you can certainly apply these tools.
Okay, thank you.
What about Apophis?
Yeah. Say it again?
What about Apophis?
That's my dream. That's my dream. I mean,
I mean, you've already worked on that a lot, right?
Yeah. So yesterday, Jorge presented our work. So we end up with a 7-dimensional problem, which is workable. Say, I mean, we're still in the range where the number of variables could not be a problem. Now, we have been, we actually did it with the strictly non-validated tools, which are provided by Taylor integration. So it is a so-called jet transport integration, but it is a non-validated thing. So Jorge was playing for some time with the intervals, trying to check whether, our uncertainties were propagating properly and all that. But I mean, Taylor models is too slow, say, to make it practical. But that would be my dream. Thanks for the comment.
Thank you.
I think Ander has a question.
Yeah, just a quick question. Do you know if the algorithms could be run in parallel, or is it completely serial? So if I want to run like a dependency tracking problem on a quite complicated model, would I be able to use that large computer to get my answer quicker?
So I am a serial guy. I mean, as far as I know, things have been, coded only for, to run not in parallel, say. Now, if you have these mincing tricks, there is nothing and then the code becomes, say, embarrassingly parallel. And then you can simply send it to lots of cores. So that, maybe that's a way of getting around that. Jorge Perez, he was playing with some ideas on to parallelize that in Taylor integration. So I guess some of those ideas can be used also for the validated integration. But aside from mincing, I have truly no idea how to parallelize. And part of the bottleneck is that essentially your Taylor expansions depend on the Taylor on the initial condition. So on the expansion point, and you have to compute. I mean, in order to compute the nth derivative, you need the n-1, and I have no idea how to do it on parallel that. But that's maybe my constraint, and maybe it is possible to do it. I have no idea.
Okay, thanks.